All right, everybody, kicking off class for this week. We have today Dan Schwartz. He is a soil scientist with the Northern Virginia Soil and Water Conservation District. Dan's experience with identifying and mapping soil types, erosion and drainage issues, and stormwater control. He's a frequent speaker not only for tree stewards, but for communities and school groups as well. And this will be a really fascinating topic, guys. So sit tight, and here you go, Dan. Thank you.
Thanks very much. Share my screen so we can get started. Hopefully everybody can see that, but if you cannot, just let me know. I can get it in presenter mode here. There we go. Okay. All right, so my topic today, of course, is going to be soils, but specifically how soils change in the urban environment, which, of course, being a resident of Alexandria or Arlington, or where I am in Fairfax County, I'm very urbanized around here. So there's a lot of changes that happen with soil when we start building on and around it. We're going to get into a little bit of that, go into natural soil, but also the alterations that we'll see in our local soils as development increases. So I like to talk very generally at the beginning about the concept of what soil actually is, because people get a little confused by it. So when normal folks think of soil, I think they probably think of a solid. You know, you're sitting in a house somewhere that's sitting on top of soil. You go to an office building that's sitting on soil. You teach in a school that sits on soil. That soil obviously has to be pretty tough stuff to hold up the weight of that building or the roadway that you use to drive there or walk there. And it is. So when we think of soil, we usually think it's a solid. But really, soil is a combination of solids, water, and gas. And you need all three of those things to make actual healthy soil. And the proportions are a little surprising to folks as well, too. So if we look at a healthy soil, an emphasis on healthy. So again, not all the soils we have in urban areas are healthy. But if you have a nice, well-tended, well-maintained soil in a garden plot or in an agricultural field, or if you go out into a natural soil like that you can find under a forest, what you're going to find is that soil is only about 50% solid, so only half solid. And the other half of the soil volume is pretty much evenly divided between gas, or what we call the soil atmosphere, and water. And of course, this proportion changes from season to season, even from day to day. Right now, we're probably looking at a soil that's 50% solid, maybe 40% gas, and the rest water, just because it's been fairly dry. If we have a long period of wet weather, we're going to have more water in the soil and a lot less available gas. But generally, if you look at soil on average throughout the year, annually, the average content of soil will be about 50% by volume solids, 25% by volume gas, and 25% by volume water. We can break it down a little bit further. Those solids, about 5% of the soil is actually organic matter. The remaining solids, 45% of the soil volume, is mineral material. And, you know, again, just even though soil is probably less solid than we might think, those 50% solids are very important. Because generally, as people, when we're describing soil, when we're describing the characteristics of soil or how soil in one spot is different from soil in another spot, we're really making comments on the changes in the soil solids. It's just kind of the way we talk about soil. It's a clayey soil. Oh, it's a nice loamy soil. Those are all descriptions based upon the soil solid content. So that's just kind of the way that humans naturally talk about soil and their differences from spot to spot. And soil solids do have an important impact on the characteristics of the soil, the suitabilities of the soil, and the fertility of the soil as well, too, which we'll get into a little bit later. But first, what are these soil solids? So what is that 45% of the soil volume of a healthy soil again? That is the mineral fraction. Well, very simply, it's sand, silt, and clay. Of course, there's rocks in soil, there's gravels, but generally when we're making a description of soil, a scientific description, we filter out those larger particles of rock and just concentrate on the sand, silt, and clay. The other 5% is the organic fraction, and that consists of the living organisms within the soil and also the dead decomposing organisms within the soil. And the 5% is not very much in terms of volume, but it's a very, very, very important fraction of the soil in terms of its fertility and its ability to grow good, healthy trees and plants. What is sand, silt, and clay? You probably have a general concept of what these things are. But, as scientists, we always like to put very hard boundaries on the natural world, for better or for worse. So there's a couple different ways you can define sand, silt, and clay, but basically the definition always comes down to the size of the particle. So I'm using the U.S. Department of Agriculture's definitions here because that's what we usually use when we're talking to groups that are interested in plants and in biology and growth. If we were talking in the engineering world, we'd probably use a different breakdown to determine what is sand, silt, and clay, but it would still be somewhat the same. No matter what breakdown you use, what kind of standard you use, the U.S. AASHTO is one of the big ones that has their own definitions of sand, silt, and clay. That's it. I always forget the acronym, but it's the American Association of State Highway Transportation Operators, something like that. It's the roads people. And they use soil a lot too, but they're using it obviously as fill underneath their roadways. So when they're looking at sand, silt, and clay, they're defining it slightly different than what the USDA is because they're looking at it as an engineering material, as a substrate to build on top of. But for us, if we're interested in trees, usually the USDA nomenclature for sand, silt, and clay is the one that we want to use. And the USDA considers any mineral particle with a diameter, so that's the width of the particle, between 2 and 0.05 millimeters to be sand. Any mineral particle with a width of 0.05 to 0.002 millimeters is silt, and any particle less than 0.002 millimeters in width is clay. Those are kind of strange numbers. I mean, 2 millimeters, that makes sense. 0.05, obviously, that's getting pretty small. Sand basically straddles the divide between macroscopic and microscopic. So a big piece of sand, 2 millimeters, you can certainly see with the naked eye. If you go to the beach, you're looking at pretty chunky sand there. And most of those sand grains, when you pick them up, they're small, but you can see them without the aid of the microscope. So they are macroscopic. Now, when we start getting down into 0.05 millimeter territory, though, then we're verging into the microscopic world. Silt is all microscopic, and clay is, it's not quite a scientific term, but it's extremely microscopic. Basically, you would need something like an electron microscope in order to see clay, a really, really powerful microscope. So when you're actually, if any of you do pottery, anything like that, worked with clay in an artistic sense, when you're holding a chunk of clay big enough to, make a pot out of or a cup, what you're really holding is trillions and trillions and trillions of individual particles of clay that are all adhered together. So you'll never see with the naked eye an individual particle of silt, and especially will not see an individual particle of clay. So the picture on the right is a pretty good approximation of the relative sizes of these things if we blew them up. Again, sand is a lot bigger than silt, and silt is a lot bigger than clay. And the analogy I like to use, which is not my own, it was from a master gardener who gave a presentation in Arlington many, many years ago. He said, if you go to the Washington Commanders game, the stadium is like a particle of silt. Your car in the parking lot, the stadium is like a particle of sand. Your car in the parking lot is like a particle of silt. And the parking pass on your windshield is your particle of clay. So that gives you a rough idea of how big and small these things are in relation to each other, even though they all seem fairly small to us. But clay is much, much, much smaller than silt or sand. Now, the soil solids together, the mineral fraction, I should say, determines an important soil physical characteristic called the soil's texture. And texture is very simply the percentage of sand, silt, and clay in a soil. So if you're feeling your soil and you're saying, I've got a nice silty clay, or I've got a loam soil, what you really are saying is, I have a certain percentage of sand versus silt versus clay in my soil. Obviously, a clay soil is going to be heavy on the clay, lighter on the sand and silt. A sandy soil will be the opposite. A loam is kind of a somewhat equal mix of sand, silt, and clay together. I'll tell you that we rarely have, well, not even rarely, you will never find pure sand, pure silt, or pure clay around here. They're always going to be mixed together to some extent. But you certainly will find clayey soils around here, and you will find sandy soils around here, and you will find silty soils around here too. But it's never going to be 100% of one particle type and none of the others. It's always going to be a little bit of mix of all three. Then we have the organic fraction. And the organic fraction consists of two things: living material. So oddly enough, anything alive in the soil we actually consider to be part of the soil, whether it's something fairly large, like your fox den, or what we think of more commonly as our soil organism, like our burrowing earthworms, our real small soil-dwelling insects, or our microscopic bacteria and fungi. And as we get smaller, bacteria being the smallest, the numbers of these individual organisms start to explode. And in fact, in some cases, when you're digging through the soil, even though bacteria and fungi in the soil is microscopic, although every now and then you will see macroscopic fungi, if you see mushrooms or the fungus growing on the side of a rotting tree log, obviously you're looking at macroscopic stuff. But most of the fungi in soil is microscopic, consisting of these little tiny white root hairs that make their way through the soil. We call them hyphae. And if we add all those hyphae together into the big network of root hairs, we call them mycelium. These hyphae or mycelium are multicellular. They can stretch out really, really long distances in many cases, but they're so small, so thin in diameter that for the most part, we just can't see them. Unless we get a whole bunch of them wrapped around each other, then every now and then they will become big enough to see. But for the most part, again, they are invisible because they're microscopic. If we had some extremely sensitive, tiny little tweezers that would allow us to pick out all these little fungal hyphae, these fungal root hairs, and lay them end to end to end, what we would find is that for every teaspoon of healthy topsoil, we would have a stretch of fungal root hairs going anywhere from about 40 yards, which is about half a football field, to about 40 miles, which is basically the distance from here to Baltimore. And that's per teaspoon. So there's just a tremendous amount of this stuff living in the soil. It's so small that we can't see it. Bacteria is a little different. For bacteria, we count individual bacteria cells because bacteria is single-celled. So each cell of bacteria is a unique piece of bacteria. So we count individuals. And for that same teaspoon of topsoil, what we find is that in a healthy soil, you'll have anywhere from about 100 million to 4 billion bacteria living within that teaspoon. So if you pick up a couple handfuls of healthy topsoil, you probably have more bacteria living in the palm of your hands than there are people on Earth. And you probably have a mass of microbial root hairs, mycelium, that could stretch for potentially hundreds of miles. So there's just a lot going on down there, but we kind of neglect it and we forget about it because we can't see it. I think humans are very visual species. We like to see things, and that helps us to understand. So we don't always appreciate the importance of these bacteria and fungi in the soils because they're just too small for us to see them and to see what they're doing. But they're there, and they're there in huge numbers, and they are very important because all this living material feeds on the dead material. So all the stuff that we see falling down off the trees now, the leaves in particular, but also, if you have a big windstorm, dead twigs and sticks are going to fall down. The tree itself will fall down eventually when it dies. So all the mass of the tree eventually makes its way back to the soil. And as you've seen as tree lovers, if you walk through the forest, you'll see tree, maybe it's fallen recently, it's still pretty intact. Come back a week later, you might start to see some of that fungi growing on the side of it. Come back a couple of years later, and depending on the size and girth and the hardness of that tree, it's going to be really breaking down by that point. And probably 10 or 15 years later, it's been pretty much consumed by the soil, and it's become part of the soil, completely broken down. And that's because of all those living materials within the soil, especially all those bacteria and fungi. What we tend to find when it comes to bacteria and fungi is that soils are more dominated by fungi in forested lands, because fungi is very good at breaking down hard, woody debris. So when a tree falls, why does the fungi grow on the side of it? Because the fungi is very good at breaking down those cellulose-rich cells within the tree, all that hard, tough stuff. Bacteria can do it, but isn't as good. Bacteria is better at breaking down sort of your soft, juicy things. So think of your compost pile when you're throwing in kitchen scraps. Bacteria are really good at breaking down those soft, juicy kitchen scraps, the banana peels, the trimmings from your kitchen. So we tend to find that soils in places like native pasture, where there's manure dropping, farm fields, and prairie lands, which are dominated by grasses rather than trees, they tend to be more dominated in the soil by bacteria. But regardless of where you are, whether you're in a native grassland or a native forest land, you're still, regardless of which of those two is dominant, you're still going to be finding literal tons of bacteria and literal tons of fungi growing in the soil. The numbers will still be huge, regardless of which one is huger, relatively speaking. But the general rule is the more hardwoody debris you have, the more fungi you're going to find in your soil because they're so good at breaking down that stuff. So the living material breaks down the dead material and it creates what's being held by in this gentleman's hand. It creates basically humus or kind of finished compost, that nice dark stuff that you find near the top of the soil. That's sort of the end product of microbial breakdown of dead organic material. That's the solids. And then we've got our air and water, the other 50% of the soil volume. 25% air on average, 25% water on average. The air and water in soil is often different than our surface waters and our atmosphere that we're breathing right now. Generally tends to be more heterogeneous, and that's because there's a lot of spatial variability within the soil. Soil isn't necessarily like one big room like the atmosphere is, where everything kind of intermixes. There's a lot of sort of discrete, closed off little pockets, little holes, where inside that somewhat segregated, pocketed little void space in the soil that is filled with air and water, the bacteria and other organic materials and other living organisms that are active in that little pocket will change the content of the air and water in there. So generally, if you think, let's say we have a nice little chunk of leaf that gets buried in the soil in kind of a unique little closed off section. There's bacteria there. They're going to want to break down that leaf. Fungi want to break down that leaf very quickly. Most of the bacteria and fungi in soil are oxygen breathers. They're aerobic organisms. They'll use up the oxygen within that little void space, that little pocket of soil, and they'll create an atmosphere in there that's more rich in carbon dioxide as a result. We tend to find that a lot of the water in soil can often be a little bit acidic as well, too, because of the actions of some of these organisms, too. So, you go from one pocket of soil to the next, and the characteristics of the air and water in each of those pockets is going to change a little bit, and it's not going to exactly match what we are breathing and drinking up here on the surface. But one of the general rules is the atmosphere in the soil generally has a lower oxygen content than the atmosphere above the soil where we are. So in our nice, natural, healthy soil, where we've got 50% solids, 25% air, 25% water, it's this division that really is helpful in giving the plants what they need in order to survive. If you have a soil that closely approximates this breakdown of solids, liquids, and gases, chances are your plants are going to be doing pretty well. And that's because they need the solids, they need support. You think of one of our taller canopy trees, like a sycamore, they could grow up to maybe 120, 150 feet high in some cases. They've got these big limbs stretching out, big leaves. When they catch a gust of wind, that's a lot of force pushing against them. So they need something pretty solid to anchor their roots into so they don't fall over every time we have a windstorm. And the soil, even though it's only 50% solid, is still pretty tough stuff. It gives that solid base of support to our trees so that they can stay upright even in gusty conditions. But you also need enough water and air, obviously, to keep the roots healthy. You need the plant to stay hydrated, and you also need to provide adequate nutrients to the plant as well, too. That's a little strange to think of. The gas and the water don't provide the nutrients, but plant roots only take up two things from the soil. They take up oxygen, and they take up water. And that way they get their nutrients from the soil is those nutrients have to be dissolved in the water. Plant roots don't take up anything solid. They're not munching on little particles of sand, silt, and clay. They're not munching on little pieces of organic matter in there that will give them the nutrients they need. They're just drinking water and taking in air, oxygen. So any nutrient they need has to be dissolved first. And if it's not dissolved, they won't be able to access it. You also need enough water and air to keep the microbes happy and active. Again, not all, but most of the microbes that we find in our soil are aerobic. They are oxygen breathers like we are. There are some microbes that are anaerobic. There are some aerobic microbes that can find oxygen from alternative sources when the soil does get very wet. But generally speaking, most of the microbes in the soil would prefer to have an oxygenated environment. They also like a damp, moist environment. They're not going to do very well when things are very, very dry. And oftentimes when things do get very dry, they go dormant. And they'll stay dormant until we get a good rainfall and it kind of lubricates everything in the soil again and brings that ecosystem back to life. So how does the soil get this nice balance of 50% solids, 25% water, and 25% by volume of gas? Well, we talked about soil texture before, which is the percentage of sand, silt, and clay. The other really important physical characteristic of soil, the second important physical characteristic of soil is something called the soil structure. And this refers to how the soil solids are arranged together spatially. Basically, how does the solid material in soil clump together? If it clumps well, you've got good structure. If it clumps poorly, you've got bad structure. And I know that sounds kind of strange and vague, but we'll get into what each of those things mean. What is good structure and what is bad structure? But first, just a little about soil structure. Again, it's how the soil aggregates, how it clumps together, how it adheres to itself. When we're looking at soil, it looks solid, but what we're really looking at is almost like a bowl of cereal. We look closely at soil and start picking it apart. We'll see that soil consists of these little discrete aggregates, all resting up against other aggregates. What is separating one aggregate from its neighbors is a pore space. Around the outside of our aggregates, we have what we call macropores. And on the inside of the aggregates, we have micropores, and the name just comes from the size. So the macropores around the outside, separating one aggregate from another, are basically larger pore spaces. And these are generally the pores that allow water and oxygen down into the soil. Inside the aggregate are micropores. They're very fine pores, very fine diameter. These are sort of your wicking or capillary pores. If you think of taking a dry paper towel and dipping the tip of it into a bowl full of water, what do you see? You see that water start to slowly creep up the fibers of the paper towel. That's kind of what happens to water inside of the micropores. They creep up there. The water is kind of attracted to the surfaces of the sand, silt, and clay that make up that pore. And sometimes that attraction is stronger than the downward pull of gravity. So the water actually creeps up and is held inside of those micropores inside. So those micropores can provide some good long-term storage of water, which is what helps our plants stay alive even when we're going through a bit of a drought. Here's some actual pictures of unique soil structure. Oftentimes we'll find what we call granular structure up in our topsoil, where we have a lot of organic matter. It's a good name because they just look like little granules. I think they look a lot like grape nut cereal, if you've ever seen those. So you oftentimes see those kind of grape nut shaped and sized little chunks of soil up in the topsoil right below our feet. As we get deeper into the soil, we'll often find blocky structure, which is basically the same shape as granular structure, just bigger. You can have sometimes really sharp angular blocks, but most of the time we have sort of this kind of sub-rounded look like you see in the photo right here. Unfortunately, what we do find a lot of in urban areas particularly, but also in plenty of agricultural fields, is what we call platy soil. And platy soil is a type of structure that often forms when humans compact the soil, when we press down on top of the soil with a big weight, and we take those blocks or those granules and we basically squash them into these tight interlocking, almost pancake plate type structural units. And we'll get into why platy soil can be a problematic soil in just a few slides. And those last two examples of soil structure, massive or single grain, those are basically soils that are lacking any structure. A massive soil is basically a soil that's all one big chunk. There are no beds. A single grain soil is a soil that is not aggregated at all. So there also are no beds, but it's just loose dust. The closest you can get to natural single grain soil is if you go to one of our Atlantic beaches around here, Ocean City, Virginia Beach, things like that. You don't find it too often, but in urban areas, you can find single grain soils from time to time. And again, usually it's because of human interference. How is soil structure created? How do we go from these individual particles of sand, silt, clay, and organic matter and cause them to bunch up together into these granules or blocky shapes or platy shapes? Well, you need kind of an interaction between binding agents, basically things that glue stuff together, and what I'll call generally burrowing agents. That's not an official term, but basically natural forces that break things apart. If we only had binding agents, all the soil would be massive. It would just be one big chunk, like I showed in the previous slide. If we only had burrowing agents, any chunk that formed would eventually just break down into single grain soil. So we need kind of both, something to hold things together, but also something to break things apart to create the pore spaces between the individual aggregates. So what are those binding agents that cause aggregation? Probably the two most important are clay and organic matter. You think of clay, it's a very sticky material. Think of soil humus or compost. It's not as sticky as clay, but it does a pretty good job of binding stuff together as well, too. Microbial decomposition creates a lot of interesting materials that have sort of a sticky type of consistency, a viscous sort of consistency that helps bind things together as well, too. And then actually fine root hairs. So both the root hairs, the hyphae of the fungi, as well as the fine roots of plants help to bind things together too. They basically act like twine that works its way through the soil and helps things sort of combine together and collect together, and it binds them up. Then we've got our burrowing agents, and these are the things that create the pore spaces that work their way through the soil and create open spaces for air and water to fill. Most famous one, of course, is worms, and they are great burrowers. They're basically burrowing their whole life. Roots are the other big one too. Even in a healthy, thriving plant, it's constantly sending out new roots during the growing season, little small feeder roots, and those feeder roots will then die back. So there's a constant flux of growing and dying roots, growing and dying roots. And when those roots die, they decompose and they leave behind a root channel that is now a pore space. There's plenty of other burrowing organisms in our soil as well, too, insects, beetles, things like that, roundworms. And then there's the non-biological forces, the wetting drying cycles, the shrinking swelling cycles, and the freeze thaw cycles. When soil gets wet, it generally swells up just a little bit. And when it gets dry, it shrinks down just a little bit as well, too. There's certain types of clays in the soils that have a very high ability to shrink and swell. So these will swell up to quite a bit larger than their normal size when they're wet and shrink down quite a bit when they're dry. If you think of kind of looking at the surface of a dry lake bed or a dry creek bed, oftentimes you'll see this kind of odd geometric shattered pattern in it. That's caused by shrinking and swelling and the wetting and drying cycle. And when it's dry, of course, it's shrunk up. So then you see big cracks forming on the bottom of that lake bed. When that stuff gets wet, it'll swell up again and those cracks will disappear. Freeze thaw cycle is kind of seeing it right now. It's not quite freezing, but it's getting cold now if you've gone outside today. When things freeze, they actually expand because the water expands. Ice is less dense than water. So water freezing in ice tends to puff up the soil, and then when it thaws, it kind of collapses back down. But these sort of cyclical wetting, drying, shrinking, swelling, freezing, thawing cycles, which tend to puff up and shrink down soil, will eventually, over many seasons, create good pore space. So all those things combined together will help create your good soil porosity, your good soil structure. Now, how does soil itself, soil as a whole, come to be? Soil always starts off as a parent material of some sort, like an unweathered bedrock or unweathered sediment that gets deposited during a flood. It takes a while to turn that into soil. And the forces that act on that unweathered parent material go by the rather inarticulate, well, articulate is not the right word, but it doesn't exactly roll off the tongue acronym of CLORPT. But the fact that it doesn't sound like a great word makes it memorable. And if it's memorable, that makes it a good mnemonic device. So hopefully if you can remember CLORPT, you remember what the 5 soil forming factors are. I think of CLORPT as being like the sound that a pebble makes when you throw it into the middle of a pond, CLORPT. So again, remember that, and hopefully you remember the 5 soil forming factors. CL stands for climate. O stands for organisms. R is relief. P is parent material, and then T is time. It's the interaction of these 5 things that create the variety, the great variety of soil that we see around Arlington County, Alexandria, around the state, around the country, around the world. When we're talking about climate, of course, there's many things that go into climate, but the 2 biggies are temperature and precipitation. And what we generally find is that the hotter and wetter things are, the hotter and wetter the climate is, the quicker materials break down, both mineral materials. So the quicker a big chunk of granite bedrock would break down into sand, silt, and clay, and the quicker a banana peel would break down into soil humus. So we tend to find that soils in hot, wet environments, tropical environments, or even our sort of subtropical, fairly humid environment that we have here in Virginia, tends to make really deep, highly weathered, and fairly acidic soils as well too. Whereas if you go up to a much colder and less rainy environment, less humid environment, you'll often find soils that have higher pH because things have not been weathered out of those soils, less clay, just an overall less weathered soil in those colder, drier environments. Organisms, the things living in and on the soil, the trees above and all the microbes down below and everything in between, are very important for both the addition and the breakdown of organic matter into the soil. Trees are great adders of organic matter. They are constantly pumping out organic matter through their roots into the soil to kind of goose the microbial populations in the soil, because a healthy population of microbes is actually a good thing for the plants and helps to make them healthier as well too. So they're adding organic matter. Plants are adding organic matter, both through the obvious means, through leaf fall, through the fall of the plant itself when it dies, but also through directly exuding organic matter through their roots down into the subsurface of the soil. And once in there, all those billions of bacteria and fungi and other critters living in the soil break down that material. And as they break it down, they, of course, are feeding themselves, but importantly, they are also cycling nutrients. They're processing and releasing nutrients from that breaking down organic matter that go out into the soil and then dissolve in the soil water, where it can then be taken up by the plants again. So they're an important part of the nutrient cycle, sort of the linchpin of the nutrient cycle, I should say. Relief is another word for your topography or your landscape position. And this is probably the most intuitive one. Where you are in terms of your relief, in terms of your landscape position, really determines whether you're going to be facing natural erosion or natural deposition of materials. A soil that forms on a very steep slope will be a naturally eroded soil. It's probably never going to get very thick and deep, because every time you have a big rainstorm, water flows off that steep slope, strips off a little bit of the topsoil via erosion. And where does it go? That eroded material goes where all water goes, downhill. What do we have downhill? We've got our floodplains and our valleys, and this is where we tend to find really thick, deep soils, because that's a natural area of deposition. Materials erode off the steep slopes. They go down to those flat valleys in the bottom. The water spreads out, settles out, and drops its sediment load and builds up those floodplain soils and makes them very, very deep. Parent material, so the material from which the soil weathers. We get a lot of our traits from our parents. Soil gets a lot of its innate traits from its parent material. And this affects a lot of the chemical and physical traits. There's certain soils that have a lot of iron in them. And the reason for that often is because they eroded from an iron-rich rock that just happened to have a lot of iron in it. So as that rock erodes, iron is released, iron oxides are formed in the soil. There are other types of rocks that, when they break down, they tend to create really sticky clays. I don't know the chemistry behind it, but they just do. We have a soil rock type around here called diabase. And if you're unlucky enough to have your house on top of diabase, you're basically going to be poking around in your yard in what feels like pottery clay, because that's just what happens when diabase weathers. It makes this really sticky, plastic, stringy clay. On the other hand, if you are sitting on top of a rock type that has a lot of quartz in it, quartz is one of the toughest rocks we have out there. Quartz basically is forever. Quartz breaks down into smaller pieces of quartz, but not much more than that. If you're sitting on top of quartz, you're probably going to have a very rocky, gravelly, sandy soil, because basically the only thing that quartz does is break down into smaller and potentially sand-sized pieces of quartz. It's not going to really break down into silt and clay, because it's just too tough and hard to do that. And then time is your master variable. It takes a lot of time to take that big chunk of granite bedrock, for instance, and break it down into those little 2 millimeter or smaller diameter or width sizes of sand, silt, and clay. And the general rule we go by, obviously this is a gross generalization, is that it takes anywhere between 100 and 500 years to create every inch of soil. People hear that and they despair a little bit, because let's say you have bad soil in your yard and you find it hard to grow things. Does it mean you're going to have to wait 200 years in order for that soil to be better? No. It might take you 200 years to create a new inch of soil, but that's not what you're trying to do when you manage your soil. What you're trying to do is not create new depth, but take the depth that you already have and make it more fertile. And fertility improvements you can do within a growing season. So don't worry about building new soil. Worry about taking the depth of soil that you have and making it better, making it more fertile and a better environment for your plants. Now, as chlorp, as these 5 soil forming factors work their magic and break down parent material and create soil, what we find is it creates sort of a layer cake. Soil is naturally a layered system, and we call each of these naturally forming layers a horizon. So each unique soil layer is called a horizon. So up at the top of our soil, what often people don't even think of as soil itself is what we call the O horizon. O stands for organic material. So the loose, beginning to decompose organic materials on the surface is actually a layer of the soil. Of course, we can see the O horizon best in forests, where we see that nice forest duff layer dominated by leaves and twigs. And it's not really the fresh leaves right on top, the ones that fell down today or yesterday during that nice wind that we had on Sunday evening. It's really the layer just below that. If you pull off those freshly fallen leaves, what you find below is a layer of leaves and twigs that are beginning to moisten, beginning to darken, and beginning to chip up into smaller sizes. That means they're beginning to decompose. And that's really the start of the O horizon. It's that organic material that's beginning to show the signs of decomposition in place. Where most people do think of the soil as starting is down here in our A horizon. That's our first subsurface layer. So it's the first layer you hit when you start digging below the surface. Most people just call this topsoil, and that's a perfectly good name for it because it's right there at the top of the soil, right at the interface between the surface and the subsurface. Topsoil is usually easy. Your A horizon is usually easy to find the start and end of it just based upon its color, because it's going to be a dark brown or black color. And the reason for this is because it's full of soil humus. As the organic material in the O horizon breaks down, it eventually decomposes so much that it becomes humus, which is basically like nature's compost. That's pretty much what you're trying to create when you're composting. Humus and compost have that nice dark brown, cocoa brown to black color. So the A horizon has that color too, because it's got a lot of this humus in there. Now, I use this picture because it shows the layers really well, but the depths of these layers are going to throw you off a bit. In Virginia, natural, even healthy soils will generally only have about 2 or 3 inches of A horizon. That's just what we get in the climate that we have here. You go to Iowa or Illinois or any of the other areas that had native prairies, you can find in the healthy soil 18 inches of A horizon, which kind of explains why so much farming is done out there. But in Virginia, nice healthy soil will only have about 2 or 3 inches. So don't despair if you don't have a thick A horizon. And the A horizon in this soil is looking particularly thick, but that is very unusual for what we'll find in Virginia. So don't let this picture throw you off. Don't think that this is the norm. Below the A horizon, we may have an E horizon. I'd say you'll find this in less than 50% of our local soils. But some of you will find it. And it's basically a leached, pale, washed out looking layer that comes right below the A horizon. In terms of averages, it's about the same thickness as the A horizons we find around here. So again, this picture will throw you off a little bit, but 2 to 3 inches on average for an A horizon is pretty typical around here. And if you have an E horizon, it's probably going to be about 2, 3, 4 inches thick as well too. So not a particularly big layer. But basically, if you're digging down through your soil and you get that nice dark A horizon, then you find a layer below that just kind of looks like the A horizon if it lost a lot of its color. Like if you took that A horizon and threw it in the washing machine and ran it on the hottest possible temperature 20 or 30 times in a row and all of the dye leaked out, that's kind of what the E horizon looks like. And that's really what is happening in the E horizon. You can think of the E as standing for exit. Officially, it stands for eluviation, but eluviation is the natural process whereby water percolating through the soil and the natural acids that are created in the soil wash out materials and leach them deeper into the soil profile and deposit them at a deeper depth. So the E horizon is sort of the acid-washed gene layer of the soil. It's where a lot of things that give soil its color have been, over many years, washed out, leached out by natural acid weathering and deposited deeper down in the soil. So the reason it's got that pale color is because things like organic matter or iron oxides, which give our soil their rusty red, orange, or yellow colors, have been leached out of this layer and deposited deeper. Where are they deposited? Down in the B horizon. So the B horizon is sort of our catchment layer, the stuff that is leaching out of the top layers, E horizon in particular, but also the A, deposits down in the B. But the most important thing that deposits in the B horizon is clay, and then to a lesser extent, iron oxide. So you've probably heard, and maybe you've said it yourself, oh, this red Virginia clay. Well, our clay generally is not red. Why the soil is red is because when you have clay, a lot of times it's coated with an iron oxide coating. And it's the iron oxide that gives the soil its red color. Clay is usually more of a gray or kind of tannish color, sometimes brown. But the iron oxide coatings on the clay and other materials will give the soil your red, yellow, or orange color. And we tend to find a lot of iron oxides in the B horizon. Those iron oxides might form higher up in the A or the E, as the clay does as well, too. That often forms in the A or E, but over time, as water percolates through the soil, as natural acids weather through the soil, those fine particles of clay and iron oxide get picked up, driven down deeper in the soil, and deposited in the B horizon. So the B horizon, as the soil ages, will actually get thicker as more and more clay gets deposited down there and deposited at a deeper depth. So if you go to a tropical area, sometimes they'll have clay horizons that go for feet. And here, it's not unusual to find 2 or 3 feet of B horizon. So your B horizon is where the clay and the iron oxide catches. So it's going to be generally your thickest, densest feeling layer, and also your most colorful layer as well, too. That's where you find your red Virginia clays, but also your orange Virginia clays and your yellow Virginia clays and your kind of cocoa brown ones as well, too. Below the B horizon, we get into the C. The C horizon is kind of a border layer where active soil decomposition and formation and erosion and weathering is beginning to peter out. So oftentimes what we see in the C horizon is that the clay content will start to drop out, and the soil will start feeling sandier, grittier, sometimes more gravelly, just kind of drier and looser. And that's because the C horizon is kind of like the parent material. It's been physically pulverized, but it hasn't really chemically weathered yet. You don't see organic matter being deposited there. You don't see clay forming like you see it forming in the B horizon. Rather, it's almost as if, let's say you were forming the soil from granite bedrock. If you were a sculptor and someone gave you a nice chunk of granite and you were going to make, I don't know, a horse out of it or something, you go there with your chisels and you'd start chipping away at that soil. That's kind of like what C horizon is. It's basically physically pulverized granite bedrock, physically pulverized parent material, whatever that parent material is. It's kind of as you start working on it, it's the mess of little pieces of gravel, dust, and sand that you find building up on your shoes after you've taken a chisel to that big chunk of bedrock for a couple hours. So it's kind of like the bedrock that's been broken down physically, kind of powdered almost, but it hasn't really chemically changed yet. It's still bedrock. It's just not a big chunk anymore. It's these little individual particles. So it's sort of been through the wood chipper, if you will. And then lastly, we've got our R horizon, which R stands for rock, solid rock. Eventually, no matter where you are in the world, you will hit solid rock. There's a wide range in depths. If you are out in western Fairfax County or eastern Loudoun County, you'll hit bedrock within 2 or 3 feet on average in those areas. Very shallow soils out there. If you're in northern Arlington or central Fairfax County, you probably have to go down 10 or 20 feet. If you're in eastern Arlington or most areas in Alexandria, you might have to dig down 200, 200, 300 feet before you hit bedrock. So there's a really wide range in soil depths around here before you hit that solid rock. So now that we know a little bit about the layers, what would a healthy soil and plant system look like? Well, what I would like to see in a healthy soil, which would, if you have a healthy soil, you're going to have healthy plants growing on it, is you want an A horizon with lots of organic matter, particularly organic humus, which is the broken down organic matter. And you want that nice granular structure. kind of a loose granular structure. So when you're sifting your fingers through it, you should be able to see just with the naked eye those grape nuts shaped and sized granules, and they should come out of the soil fairly easy. The soil shouldn't feel very dense. It should feel kind of crumbly almost. You want to have lots of microbes in the soil because those microbes will break down organic matter that's added to it. And as they break down that organic matter, it's part of the decomposition process. They're releasing mineral nutrients that then go out and dissolve in the water. That good granular structure that I talked about, the reason it's important is that good structure means you have good pore spaces, basically. So good structure is not just about the chunks. It's about the pore spaces in between. We have these nice, well-defined chunks like you see in that person's hand right there. That means there's nice, well-defined pore spaces between each of those chunks, and that's why it's so visible to us. When you have those good pore spaces, each one of those pores is a little conduit that can allow oxygen and water to seep down from the surface into the rooting zone of the plants and also provide oxygen and water to the microbes that are in there as well too. As the water seeps down through the pore spaces between our soil aggregates in a well-structured soil, that water will dissolve the nutrients that were decomposed by your bacteria and your fungi. And when that water is there, it's full of of soluble nutrients. The plant roots will take that up. And as they drink that water, all those good nutrients go with it and go into the plant and power new plant growth. And of course, a well-fertilized plant is basically going to grow well. And as it grows well, it's creating more organic matter that it then cycles back down into the soil ecosystem. And the cycle continues because you kind of see how once this gets started, it can be fairly self-sustaining as long as you don't do anything to mess it up, which unfortunately we do quite a bit of time. Another feature of the healthy soil plant system is you want your bee horizon with lots of clay. You know, we kind of shake our fist at red Virginia clay because it can get really tough to dig through when it's hard and dry in the middle of summer. But clay is very good at holding on to water. So as some of that water percolates down deeper into the soil, that bee horizon is going to hold on to a significant chunk of it. And that chunk of water that's held down there on the surfaces of the clay can be taken up by some of the deeper roots of the plant. Excuse me. There is some microbial breakdown of organic matter and nutrient release occurring in the bee horizon as well, too. It's not going to be nearly as much as the A horizon. The A horizon is our biological powerhouse of the soil, even though it's only on average 2 or 3 inches thick. But the bee horizon will still have active microbial communities down there. It's just not going to be as concentrated. So there's still organic matter being broken down and nutrients being released, just not at the same levels you find in the A horizon, but still an important source of nutrients. Other soluble materials that are leached from the topsoil will often filter out in the bee horizon. This is good often for the soil itself because a lot of those soluble materials could be useful to plants. Like one particular nutrient that's very soluble is nitrate. You add a little nitrate to your surface soils as a fertilizer, and then it rains. Unfortunately, a lot of that nitrate is going to leach down deeper into the soil. But if we have a good bee horizon there, some of it's going to get filtered out in the bee horizon, and the plants will still be able to access it. This is also good for our water quality, because as water passes through, we want all those materials to be filtered out before they get to our groundwater, and before that groundwater flows into our surface waters. Your sea horizon, it's going to be fairly sandy or gritty. It's not a lot of water retention there, but there's some. And this water will be accessible by some of the deeper roots of the plants as well, too. So there's a good repository of water down there that the plants can access during periods of, more severe drought. And again, even though it is fairly sandy, it's not going to filter out as well as the bee horizon does. It's still, as water percolates through the sea horizon, going to filter out some of those soluble materials, allowing the water that eventually makes it down to the groundwater to be really clean and well filtered by the time it gets there. And then anything that passes through the sea horizon is basically groundwater recharge. It's on its way down to the bedrock and down to our more permanent water tables. Now, that's what a healthy soil and plant system will look like. Unfortunately, we live in an urban area, and one thing we know about urban development is it has a heavy effect on the soils and the characteristics of soils. This development causes a lot of changes, and almost all of them, unfortunately, are negative in terms of the overall health of the soil. The first big one I can think of is compaction. Basically, when we're building, we grade out the soil, we run it over with heavy machinery like this backhoe here. And of course, that puts a lot of weight down on the soil. You do need compaction sometimes. You want soil underneath your house, underneath your foundation to be compacted so it holds the weight of the house without causing warping of the foundation. But you really don't want compaction anywhere else. You don't want compaction in your front yard, your backyard. Fortunately, and especially in urban areas, the lots are so tight, it's hard to move this machinery around these small lots. During the construction process, there's a lot of inadvertent compaction of the soil where we don't want it. Front yards, backyards, other places where we're trying to grow things. And a more compacted soil makes it create more dense soil, and that can have a lot of negative impacts on the soil itself and on the plants that you try and grow on it. Basically, when a soil is compacted, it squeezes out the available pore space. When there's less available pore space, there's less room for air and water. So a compacted soil is going to have significantly more solids and less open space available to be filled by oxygen and water. And compacted soil reduces the ability of oxygen and water to get into the soil in the first place. So I call this sort of impervious light. You think of an impervious surface, asphalt, concrete, or rooftop. Basically, it does not let water pass through. A compacted soil is kind of halfway to impervious. It allows a little bit of water to pass through, but not nearly as much as it would have had it not been compacted in the first place. So if you think of your well-structured soil, a well-structured soil is basically kind of loose and light. It's got these nice granules, these nice soil aggregates that are held together pretty well, and they're often wrapped in a kind of organic material that is created as microbes break down leaves, twigs, and other things. This organic coating on the soil aggregates can actually make them waterproof. So when these aggregates get wet, they don't disintegrate, because if they did disintegrate, then they would fall apart and clog up all the pores. So they're sort of waterproof aggregates. In between those aggregates, we've got the macropores. So when it rains, there's lots of channels and pores for that water to access and percolate down into the soil. When we take that same soil and we squish it under a heavy weight, like at a construction site, we tend to compact the soil and create platy structure. And maybe it was this nice blocky structure on the left that we started with, but we squeezed down those blocks under that heavy weight of the treads of that backhoe, and it squeezes them into these tightly interlocked plates that have a little bit of pore space in between them, but that pore space is fairly small, and it would be pretty hard for water to pass through it at any quick rate. That same rainfall falls on this platy structure. A lot of that water just can't get down into the soil in the first place. Some does, but a lot of it stays up on the surface. So if you have a really flat compacted soil, you might find that it stays soggy for a long time. If you have a sloped compacted soil, what you might find is you have a lot of fast-moving stormwater runoff flowing off that soil during a storm. So you probably have seen an illustration similar to this where it shows how the infiltration of water and the runoff content of rainfall changes as you move from a natural environment to an urbanized, highly impervious environment. It's not just impervious surfaces that are making this change too. Obviously, they have a big effect as well, but it's also all the compacted soil. And we tend to underestimate the influence of compacted soil because it can look healthy. You can grow nice green grass on top of a compacted soil. That doesn't mean it's a healthy soil, and it doesn't mean that that soil is absorbing water like a good, healthy soil would. So it's sort of the silent imperviousness that we find throughout our urbanized, suburbanized landscapes. Another issue with compaction is that it creates a really dense, strong soil. So this is sort of your typical new subdivision street tree planting right here. The thing is, you think you should come back in about 20 years and that tree is going to be a lot bigger. You do come back in 20 years, and sometimes you see that the tree has grown, but sometimes it hasn't really changed all that much. It still kind of looks like this, burlapped and bald specimen tree that someone bought when the community was built. One of the reasons is in that really compacted section of soil between the sidewalk and the road, that soil might be so compacted that it is difficult, if not impossible, for the roots to penetrate. So the roots are restrained or constrained within their original sort of root ball, and they don't have the strength to push out into that dense compacted soil around. And as a result, if the roots are stunted, the tree is going to stay stunted too. It's just never going to grow very big. It's almost like a a maxi bonsai type of tree. I think a really good example of this that kind of shows the concept well is this picture from Casey Trees. This is Pennsylvania Avenue between the White House and the Capitol. And I think these are all these willow oaks, I think they are. But anyway, it's all the same species of tree. You can see the ones on the left over here are pretty stunted compared to the ones on the right. These just look healthier and fuller, especially their canopy. Why is that? I mean, the growing conditions, the temperatures, the amount of rainfall, it's all going to be the same here. They're only separated by about 20 feet. The real difference is these trees are sitting in a tree pit, and they probably have access to the soil underneath the sidewalk and the soil under the roadway. But the problem is the soil under both of those surfaces is extremely compacted. It's basically probably almost as dense as the concrete itself or the asphalt itself. So those trees don't really have the strength to push their roots out into that highly compacted soil under either of those surfaces, under the sidewalk or roadway. I wouldn't say these trees over here are living in paradise, but at least they have this 30, 40 foot wide section of soil between the sidewalk and the building to spread their roots out into. And basically a tree is only going to grow as big as its roots will grow as well too. So these trees obviously have a much greater root mass. They're getting out into the soil much more. And as a result, they're powering the growth of the tree above them as well too. A tree is always proportional to the mass of its roots underground as well. So this is kind of showing you in an extreme example how really compacted soil can constrain tree growth just by being so strong that the plant roots can't penetrate through it. A little closer to home, an example from Arlington itself. We did a study for the county a couple of years ago where they had us looking at the characteristics of what we'll call old versus new lawn soil. And basically we looked at houses and studied the lawns of houses that were built in the 50s and 60s, and then we compared them to brand new houses, brand new construction where the projects were still under bond, which means basically the builder still owned them. They had not sold them yet to the first owner. So some of them were completed, some of them were being constructed, but and very close to completion, but they hadn't yet been sold to the first resident. We looked at, amongst other things, the density of the soil and the infiltration rate of the soil. The infiltration rate refers to how quickly water will soak down into the soil. The average density was 1.37 grams per centimeter cubed for the new houses, 1.15 grams per centimeter cubed for the old. So not a huge difference, but about a 20% increase in density with the new houses versus the old. And again, this is just really as a result of the new construction that occurred. When you build a new house like this on the left, you're going to have construction machinery crawling all over there. It's going to compact the soil. That's not to say that these old houses didn't have compacted soil too. Maybe they did. Maybe they didn't have as much because it's not as big of a house, but they've also had, 60, 65, 70 years in some cases of plant growth and gardening and some care as well to decompact that soil, to reverse the effects of that compaction. The big change we saw was that the average infiltration rate. So we were looking at, again, 10 old houses versus 10 new houses, or at least 10 readings from old versus new houses. What we found for the new houses, the infiltration rate, basically the rate at which water soaked into the ground, was 0.13 inches per hour. So basically a tenth of an inch per hour. For the old homes, it was 1.28 inches per hour. So there's a 90% reduction in the rate at which water absorbed into the soil for these new construction homes compared to old homes. That can be a huge difference both for local water quality as well as for the neighbors, because the runoff from this home is going somewhere. And it looks like here it's going down to the left. There was an older house there. I think one of the reasons that Arlington asked us to do the study for them is because they were getting a lot of complaints from the neighbors of these new homes that this new home was being built, and all of a sudden they were seeing problems with flooding, with a great increase in the amount of stormwater volume running through their properties during storms. And that's because we just assume that soil is soil. If you're growing nice green grass on top like they are here, it must be soaking up water, but it's not. These compacted soils are really soaking up water just at a fraction of the rate that I'll say a healthy suburban urban soil would. And these healthier, older houses, they probably are soaking up water at a slower rate than, a nice natural forest would as well too. So there are some real big effects that come with a disturbance of the soil and compaction of the soil. Another effect we see with urban soils is mixing. So a natural soil will have these natural layers here, O, A, E, B, C, and R horizons. When a soil is constructed, all these layers get mixed together. That backhoe comes through, it digs things up. Obviously, it's not preserving those layers. Everything just sort of kind of gets homogenized together. This also causes the death of a lot of the fungi in the soil. Because remember, fungi exist as these long, thin root hairs, these twine-like little root hair hyphae. When you go digging through the soil, you tend to cut through these fungi and kill them. Mixing of the soil causes that fertile topsoil that used to be, concentrated up there in the 2 or 3 inches of the A horizon, and it disperses and spreads it throughout the depth of the soil profile. And this can be very damaging because you really do want that concentration of humus-rich topsoil up at the top, because that's what attracts a real high density of microbes and fine plant roots as well, too. And that density is what allows the nutrient cycle really to get kick-started in the soil. If you disperse that organic matter throughout the soil, that soil humus throughout the soil, you are kind of losing that critical mass of organics and microbes that you need in order to really power the nutrient cycle. So loss of productive topsoil equals a loss of microbes, a loss of humus, and a loss of nutrient cycling. You can also get some pH changes in urban soils as well, too. Sometimes it's very local. Where you have concrete, there's a lot of limestone within concrete. This can actually raise the pH of the soil under and right next to the concrete. And sometimes it can be a little difficult to grow some of our more acid-loving plants around areas of concrete. There's a lot of fertilizers that do the opposite, that lower pH, especially fertilizers that have ammonium or sulfur. Ammonium itself is a weak acid, so if you add that to soil, it will tend to acidify the soil. Also, as ammonium gets converted in the soil by microbes, a natural process, from ammonium to nitrate, it also releases a lot of acids during that transition as well, too. Sulfur, generally when people are adding sulfur to their soil, I shouldn't say that, but a lot of times when people are adding sulfur to their soil, they're actually trying to drop the pH. So sometimes if you need to drop the pH, adding sulfur fertilizers is a good thing. But if you just need to add sulfur, because it is an essential nutrient, just be cognizant that you probably will be driving that pH down a little bit as well, too. And pH is very important to plants because I used to think when I was sort of learning about soil, well, pH is important because if it gets too acid, obviously, you think of those terrible movies where people throw acid on each other and blah, 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 and, Halloween's coming up. That must be what's happening to the plant roots. All the acid in it is just dissolving the plant roots. That's not what it is. The reason that pH is important is because the pH of the soil affects the availability of nutrients. So this illustration you see here, basically where the bar of each of these nutrients, here we have nitrogen at the top, then we have phosphorus, then we have potassium. When this bar is thicker, like right here in the meaty middle, right around pH 7, that means there's more nitrogen, more phosphorus, more potassium, more calcium, and magnesium available at that pH. When that bar gets thinner, it means at the pH down here, closer to 4, really acid conditions, there's a lot less nitrogen available. Doesn't mean there's less nitrogen in the soil. It's just not in a form that is available to the plant roots. Basically, it's not in a form that can easily dissolve into the water. There's also some other things that happen. There are some things like aluminum, which is not a plant essential nutrient. It's essential for us, but not for plants. If there's too much aluminum, aluminum can actually become toxic. So at low pHs, acidic conditions, there's a lot of aluminum that becomes available in the soil, and it can become so available that it becomes a toxin to the plants itself as well, too. So again, the real reason that pH is important is because it affects the availability of nutrients and toxins. And generally, if you're maintaining a pH around here of about 5.5 to 6.8 roughly, that's kind of your sweet spot. Our native plants around here like things a little bit on the acidic side. Not a strong acid, but an acid soil nonetheless. And within that 5.5 to 6.8 or so range, you generally find that all the essential nutrients are available fairly well. Maybe they're not available at the highest possible point, but they're all there in generally the right amounts to supply the plants with what they need. And the things like aluminum that can become toxic are there in a small amount, but not in a high enough amount that it's going to become an issue for your plant growth. If you start moving outside of that pH range, though, you might start to see some nutrient deficiencies and in some cases, aluminum toxicities. Another important urban effect is salt. Now, the obvious thing is if you put too much salt in your plants, salt attracts water and it causes the plant to wilt because the water is more attracted to the plant and the water is more attracted to the salt. And then the plants have to work extra hard and provide their roots with extra suction to suck up any available water. So even a soil that has a lot of water, if you add a lot of salt to it, that water is going to be held by the salt. It's such a strong bond that the plants won't be able to access it and they'll start to wilt. But salt also does something very important. It destroys soil structure. Salt, for whatever reason, is very good at taking those nice aggregates of soil and causing them to kind of expand and disintegrate. So a salty soil often doesn't kill the plants just because the plants can't get enough water. It can kill the plants because it creates this hard, dense, structureless soil in which there are no pore spaces to allow water and oxygen to get into the soil in the first place. So salt is kind of a double whammy. Makes it harder for plants to get the water they need, and it also destroys the structure and creates this hard crust on the soil with very little pore space in it because it causes all the soil aggregates to disintegrate and dissolve and clog everything up. What is really important to remember is that healthy soil is great in and of itself, but healthy soil also leads to health in other parts of the environment. Poor soil leads to poor health in other parts in the environment. And this connection is particularly clear in the water cycle. Poor soil leads to poor water quality. A good, healthy, natural soil acts as a filter and a sponge. It lets water pass through. It holds on to a lot of that water as it passes through, and the water that is able to percolate down through the soil and enter into the groundwater gets filtered as it passes through the soil, becomes clean on the bottom. Organic matter and clay in particular are very important in this process. They actually carry small electric charges that attract opposite charge dissolved ions out of the water and cause those ions to bind in the soil. So as the water passes through, it's carrying a lot of, let's say, phosphate or nitrates because it's a farm field or a community garden that just got fertilized. We don't want those fertilizers to wash down into our groundwater and off into our surface waters. But as that dissolved material passes through the soil, those ions that are dissolved in the water are attracted like a magnet to the surface of clay and organic matter. So as the water slowly percolates through, the ions are attracted out, they bind in the soil, and the water that continues to percolate downward gets cleaner and cleaner as it goes. There can be bad bacteria, bad pathogens, viruses and such inside of our runoff. You think of what's washing off with runoff. Animal waste, think of all the pets we have around here, but think of course, our Canada geese and our wildlife as well too. They're pooping all over the surface, just like animals do. When water washes over, as stormwater runoff, it picks up some of that manure, that waste, and it can pick up the E. coli's and other things that are contained within there. If that water can then percolate through the soil, those microbes, those bad microbes that are getting washed in with the percolating runoff, are going to be attacked by all the good bacteria and fungi within the soil. And generally, those good bacteria and fungi are much more adept at surviving in the soil environment, and they kill off that bad bacteria. This is basically how a septic tank works. You put the septic effluent through the soil, you slowly percolate it through, and you rely on the natural microbes within the soil to kill off the bad pathogens, the viruses, the bacteria, things like that. Water itself, of course, is attracted to clay and organic matter. So as water percolates through, a lot of the water itself is held. Not all of it goes down to the groundwater. And that's great because we want a lot of water in our soil so that when we do have drought conditions like we had over the summer, our trees don't all wilt and die. Water has a great ability, a great capacity to, soil has a great capacity to hold a lot of water. And this allows those plants to keep drinking even when it's been a week or two since we've had a decent rain. So as the water passes down through the soil, a good portion of the soil stays in the water. That's why soil is a sponge. And the water that does pass through and goes down to the groundwater gets filtered. So soil is a filter and a sponge for our water. So it's kind of like the Brita filter of the world. The problem is, in our urban areas and suburban areas, soil is compacted. It's dense. This allows less water to enter into the soil in the first place. If water can't get into the soil in the first place, it can't be filtered and it can't be held. Instead, it becomes surface runoff. And that runoff goes generally along our roadways, along the curb, till it hits a storm drain. In the storm drain, it flows into a pipe, and that pipe, usually in older development, just drains out to the nearest street. This is my boss, Willie Wood. He is 6'6". He's a very tall guy. He's standing in a fairly small stream, but you can see his feet are not on the bottom, and his head is well below the top of the bank. This is a classic sign of an urbanized stream. The reason the stream looks this way with this very steep, bare bank is because it's eroding. And the reason it's eroding is because every time we have a major storm, we get a ton of stormwater runoff that normally would have not have become stormwater runoff. It would have percolated down into the soil and become stored and filtered in the soil. But instead, we've got all this compacted soil. We've got all these impervious surfaces that is preventing water from getting into the soil in the first place and increasing the amount, the percentage of that rainfall that becomes stormwater runoff. Then we've created an easy channel, an easy pathway for that water, the curbs and the storm drains, to get from our roads, our houses, our driveways, our sidewalks into the stream. Basically, what this does in aggregate is it creates almost a little mini flash flood through our streams every time it rains. And that flash flood tends to erode and incise the stream. So the stream gets wider and it gets deeper. And that's what you're seeing right here. A nice, natural, healthy stream generally does not have bare banks. You won't see bare soil. You'll see stuff growing on it, and you'll see a much gentler slope and a much less of a total depth from the top of the stream to the top of the bank there. Especially if you're seeing plant roots like this hanging out in air. We all know that roots grow below ground, so that means that the soil that probably within a couple weeks ago was covering this root mass has eroded away and leaving these plants, these roots exposed. So as a recap of what urban effects are on soil, urban development tends to create a dense soil through compaction. This reduces the amount of pore space available in the soil. And with less pore space, you reduce the amount of oxygen and water that can get down into the soil and be available to the roots and to the microbes. This also causes an increase in surface runoff and erosion because the water is no longer absorbing down into the soil. Compaction creates a strong soil. This may restrict root growth because the soil may be so dense that the roots don't have the force to penetrate through it. Urban development disperses and degrades topsoil and humus content. It tends to take that topsoil and kind of homogenize the soil, mix that concentrated topsoil humus area in with the rest of the depth of the soil, thus decreasing that density of fungi, bacteria, and organic matter we have at the top. It can sometimes change the soil pH, both for the higher, meaning more basic, or for the lower, meaning more acidic. And it can cause the soil to become salty and dispersed as well, too. So basically, all in all, urbanization typically degrades the fertility and ecological functioning of the soil unless we do something to correct that damage. So what can we do? Well, there's sort of a new paradigm of plant health being pushed hard by the U.S. Department of Agriculture, which is a really good thing because they were sort of the creators of the old paradigm. And the old paradigm was basically a chemical-based one. It's like, oh, you're lacking something? Add fertilizer. Oh, there's too much of a bad thing in here? Pesticides and insecticides will fix that. Now what they're emphasizing, and obviously they're focused on agriculture, they're focused on big growers, but the thing that works in a farm field is going to work perfectly well in a suburban garden plot or just in a natural planting bed of trees or other ornamentals. Basically what they're saying is do stuff to the soil that will feed the things that naturally live in the soil, the worms, the small critters, the small arthropods and insects, and especially the bacteria and fungi. And if you can feed them, they will do a lot of the work for you to make your soil more fertile. So basically, puff up the health, the size, and the activity of the natural organisms that live in the soil and let them do the soil health building for you. So how do we do this? Well, I kind of sound like a broken record when it comes to soil health and how to make soil healthier. But basically, my panacea cure-all for all things soil related is add organic matter. And the reason for this is that organic matter is the base of the soil food web. All the stuff living in soil, it's the very base where all the energy originally comes from is decomposing organic matter. The leaves, the twigs, the manures, the dead animals, the carcasses, the falling trees that all naturally would fall on the soil surface. These provide the organic carbon and the nutrients that power the ecosystem below, inside the soil, below our feet. Organic matter is also one of those natural binding agents, those gluing agents. So the more organic matter you have, and especially as it breaks down into soil humus, humus is really good at promoting soil aggregation and getting good structural development. If you have a hard, dense, compacted soil and you start mixing in organic matter, over time, it's a slow process, but over time it will start reforming that good soil structure again, that good granular structure, that good blocky structure. So nice aggregates that are held well together, they're coated in that organic matter, a material that tends to make the soil aggregate fairly waterproof, meaning it won't dissolve in moist conditions or really saturated conditions either. And also, as you start getting that good aggregate formation, you're also getting the formation of those big pores that separate one aggregate from the other. When you get those pores, then water can start getting back down into the soil, oxygen can start getting back down into the soil too, which, again, when soil is compacted, it's much harder to do. Organic matter is also really good at increasing the water and nutrient holding capacity of the soil. So not only is organic matter sticky, it's attractive to water and it's attractive to dissolve nutrients. They will bond to the surface of that organic matter and create a sort of a bigger sponge, if you will, that has gives the soil a greater ability to hold on to those two materials. And it decreases the density of the soil. Organic matter, especially soil humus, is very low density. So you mix it into your soil, you make the soil less dense as well too, which of course is a very good thing when you're dealing with compacted soil. For that second to last bullet point, the increase of the water and nutrient holding capacity, I wanted to show you a little graphic which kind of illustrates it. So what's important in soil is not the total volume of water in the soil, but the amount of water that's available to your plants. And what you'll see is there's two important levels of water. There's something called field capacity, and there's something called the wilting point. The wilting point is sort of self-explanatory. It's the volume of water in soil below which plants will start to wilt. Field capacity is a little bit different. It may not be a concept you've heard of before, but I like to think of a wet sponge. Basic field capacity is basically the maximum volume of water that soil can hold against the pull of gravity. And the way I like to visualize it and describe it is with a dry sponge. You go and get a dry sponge from Safeway or whatever shopping center. You take it home. Let's say you turn on your faucet very, very slowly so it's dripping. And you just drip water onto that dry sponge. What happens for the first 30, 45 seconds or so? That sponge starts to expand. It's absorbing those drips of water. For the first 30 or 45 seconds, all the drips are absorbed by the sponge. You don't see any water coming out of the bottom. Eventually, though, you do see drips coming out of the bottom. All the pore spaces within that sponge are full. You turn off the faucet, that sponge is probably going to drip for another 10 or 15 seconds or so, and then it stops. Still a lot of water in there, but it's not dripping out, and that's because all the water that's left in there, it's more attracted to the surface of the sponge. That attraction is stronger than the downward pull of gravity. That's basically what field capacity is. When you fill a soil up with water, the water will be attracted to the surfaces of organic matter, sand, silt, and clay, and other solids that are in there. And it's also being pulled downward by gravity. Field capacity is the maximum amount of water that a soil can hold against the pull of gravity. So that wet sponge, when it stops dripping, it's at field capacity. A soil is at field capacity about a day or two after a hard soaking rain. So during that first day after the hard soaking rain, you're going to have consistent water draining down. It's held so loosely, all the pore spaces are filled with water, that water is held so loosely that it's more attracted to gravity. Gravity has a stronger pull on it than its attraction to sand, silt, and clay. But after a day, the water that remains is more attracted to the sand, silt, and clay. That film of water around the sand, silt, and clay has narrowed enough that the force of attraction is stronger to the soil than the force of pull from the gravity is. Now, these are important because the volume of water available between the wilting point and field capacity is your plant available water. This is what the plants have access to. This is what the roots can get. The reason that this is the case is because above field capacity, any water that you add above field capacity, it's going to immediately drain out down into the groundwater because it's just being pulled down by gravity. So it doesn't stay in the soil long enough for the roots to access it. Any water held below the wilting point is actually so attracted to the surface of sand, silt, and clay that the roots don't have the force to suction it off. What you'll see is that naturally the soil texture has a big influence on how much plant available water there is. Sands hold very little water in total, but they also, any water that they hold very loosely. So the wilting point in sands is very low. If there's any water in sands, almost all of it is available to the plant because the sand holds it just very loosely. But the total volume of water that a sand can hold is just very low. So sands make almost all of their water available to plants, but the amount of water that is available is not much. Clays, on the other hand, they hold the most water at field capacity. You see, it evens out here. It kind of flattens out, but it's still increasing. So clay holds the most volume of water. But clay is kind of greedy. It holds that water very tightly. It holds it very close to its chest, and it doesn't share it very well. So the wilting point actually increases greatly in clay. And there's still, a good bit of water here. But really, your golden texture is loam, because loam has a little bit of sand, silt, and clay. So it's got kind of all the benefits of all of them. It doesn't hold the total volume of water that clay does, but its wilting point is much, much lower. So the distance between these two bars is the greatest, and that means the plant available water is highest for a loam. But the problem is, you don't have much say about your soil texture. If you have a sandy soil, hate to say it, but you're pretty much stuck with a sandy soil. If you have a clay soil, you're pretty much stuck with the clay soil. There's not really much you can do to change the texture. What you can do is add organic matter. As that organic matter decomposes and becomes soil humus, this is the effect it has on the field capacity and the wilting point, regardless of your original soil texture. Organic matter, particularly soil humus, tends to greatly increase the field capacity and only slightly increase the wilting point. And this is because humus is like clay in that it can hold a lot of water. Humus is unlike clay in that it holds that water very loosely and makes most of the water it holds available to the plants. So adding soil humus to any soil, regardless of the original texture, whether it's a sand or loam or a clay, will greatly increase the amount of plant available water available within that soil itself. So that's sort of the general role that humus plays in increasing water holding capacity in your soils. So how do you kickstart the soil biology, especially the bacteria and the fungi? And once you're kickstarting the soil biology, you are also, by just natural processes, also kickstarting the soil food web, starting that cycle. As soon as anything starts growing in the soil, there's something out there hunting it and trying to eat it. Well, I say the first thing you do is plant. Just plant, plant, plant. Plant densely, plant frequently, plant often. Because the more living roots you have in your soil, living roots exude naturally organic matter into the soil. Living roots and the mass of plant above them also help to protect the soil. If you have a well-planted soil, densely planted soil, that's a soil that's going to be very hard to erode. It's going to be very hard to wash away that topsoil. The more living roots you have, the more pore spaces you create as well too, because living roots are constantly, even in a healthy plant, growing and dying back, growing and dying back. And each time it dies back, you've created a new pore space, a new channel for air and water to access to get down from the surface into the rooting zone. But other than just plant, 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 which again, I think is the best way to add organic matter to your soil, there are other specific things that you can do. I'm going to kind of go from simple to more complex. One very simple thing is not to rake your leaves. You can leaf cycle. Rather than raking your leaves, you can just chip them up with the mower and leave those chipped up leaves on the surface of your lawn. If you chip them up to about dime size, they will settle between the blades of grass and they won't smother your lawn. There was even a study they did at the University of Michigan Extension where they mowed 18 inches of leaves into a lawn. And if they chipped it up small enough, it did not smother the lawn. You can mulch. Mulch is a very good thing, especially to put around your big specimen trees, things that you really want to protect. Because wood mulch actually does a pretty good job of simulating the type of materials that would be falling to the surface in a forested environment. If you have grass growing up to the trunk of your trees, that often puts the grass roots and the tree roots in competition with each other for available water and available nutrients. Big specimen trees like this one here, they tend to prefer mulch around their base. And if you can, put that mulch all the way out to the drip zone, but obviously that's not possible for everybody. But the trees will appreciate it. And if you can only put a 10-foot diameter circle of mulch, so be it. But if you can go 20 or 40 feet, the trees will be happy. Mulch also does a very good job of insulating the soil as well, too. It prevents extremes of heat or cold because it kind of acts like a blanket. It also holds in a lot of moisture as well, too. You can do something like compost top dressing. Again, we're going from sort of the least effort to the most effort. This is in process right here. Compost top dressing is basically when you rake out a thin 1/4 to a 1/2 inch layer of compost across your lawn or across your other planting beds. Again, thin enough that it's not going to smother any ground covers that you have. So this is a landscaping company that's laid out these piles of compost that they will eventually come in with a crew of to rake out into a very thin layer so that the grass is poking through. But that's an easy, well, I shouldn't say that. It's a quick way to get a lot of humus into your soil very quickly, but it is quite a bit of effort. And then, if you do have a really bad soil, sometimes you need to kind of start from scratch and break it up. I would say in most cases, you don't need to do this, but let's say you had something like a patio that you removed and you want to figure out what to do with the soil underneath. That soil underneath is going to be very, very compacted, and you probably would have to go in and break it up and till it up. Generally, I say limit tillage to really, really bad soils, even in garden plots. Limit it to really bad soils, because every time you till, if you do have good soil structure in there, you're kind of chipping up that soil structure. But it is a good way to decompact really, really compacted soils. But when you're tilling, I always say add in organic matter. If you just till, you're not going to be doing much good. If you're tilling and adding in a good bit of compost at the same time, then you're getting that organic matter down into this newly loosened soil, and you're going to start kickstarting that soil food web in a much better way. And sort of an extreme example of this tillage of really compacted soil is something called urban soil rebuilding. What I'm going to do is stop sharing just for a second and see if I can pull up this video of urban soil rebuilding in Arlington. So urban soil rebuilding, oops, here's a video of it, is what you can do for just really, really terribly compacted, kind of lifeless urban soil. So this is an Arlington County project. They were doing this urban soil rebuilding in what we call the hell strip, or the suicide strip, between the sidewalk and the roadway at George Mason and Lee, well, not Lee Highway, I guess it's Langston now. But basically what it is you layer out a thick layer of compost on top of this compacted soil. And then you use a backhoe to basically scoop and dump. So you put the bucket of the backhoe down into the soil, and that tends to mix that layer of compost that you put on top with the compacted soil below. You raise up the bucket, and then you dump that material out, and that naturally tends to mix it a little bit and break up the big compacted soil clods that are in there. So this, you can tell you need heavy machinery to do this, and this is really only something you would do if you have access to that machinery and your soil is in really, really bad shape to begin with. So it may not be something that you would do in a residential property, but it is something that we're seeing in Fairfax County. I know obviously here Arlington County is doing it. So the municipalities have started to do it. So I'm just going to show you what it looks like real quickly. This only lasts for a couple seconds. There he's scooping and mixing in the compost. Bring it up and dump it and give it a shake. And you basically do this until the entire soil has been mixed and decompacted. And this tends to create kind of veins or ribbons of compost that go down into the soil and provide highways or pathways for water to get down in there. Let me get back to my slideshow. There we go. So urban soil profile rebuilding, pretty interesting, but again, something that probably not too applicable, except in the worst case scenarios. I did want to talk about a few technologies that are specific to urban street trees. So again, this is not necessarily something that you would do on your own property, but you might see projects like this in an area like Alexandria or Arlington, where the county government is trying to reintroduce street trees in certain areas, certain neighborhoods. One thing that we see quite a bit of is something called structural soil. And it's sort of a compromise material between the urban needs and the plant roots. And basically what it is, it's a mix of soil, very organic rich soil, so compost rich soil, and very angular stone particles. And what they do is they kind of put this mix of stone and compost into the tree planting pit on the sidewalk, or between the sidewalk and the roadway, and compact it a bit. And what happens is, because they're using these really angular stones, they kind of interlock with each other. One sharp angle on one stone rests on another sharp angle of another stone, and this rests on another stone. And this results in a lot of pore spaces between those stones that can be filled with soil, air, and water. So in a way, the angular stone particles are there to create a lattice to hold up the weight of the concrete, the sidewalk above it, while also allowing these sort of uncompacted small pore spaces to be preserved between these stones that can be filled with air, water, and soil, and also can be filled with plant roots. So the fine plant roots can go through those uncompacted void spaces in between. So this is an example of structural soil. It kind of looks like fresh asphalt, but it actually is just structural soil. They ripped off a section, a paver of the concrete sidewalk, put down the structural soil, and they haven't put the concrete back yet. But the reason they did this is they planted this new tree here, and they knew if they just used regular concrete with a compacted base, what they would get is, the plant roots would try and grow under there. They'd have a hard time doing it. The plant would probably stay stunted. But as the plant root did grow, it also would push up the concrete and break it. So now you got to fix the concrete, and you've still got a plant that's not healthy. This basically, the structural soil provides a healthier, easier plant medium, a growing medium for those tree roots to pass through so that they can access all this much less compacted and open soil on the other side. So chances are, if we came back to this tree in 20 years, it's probably going to be growing pretty well, because its roots are going to be growing out into the soil, and they're not going to be constrained as they normally would, and just be growing in that hell strip between the roadway and the sidewalk. Tree box filters are another thing you see that, again, is kind of a compromise between urban needs and the plant roots. So the tree box filters are basically an underground vault for the roots, and they have this lattice work of plastic, or sometimes it's metal. And then it's paving on top, so it can either be a roadway or a sidewalk. The lattice work holds up the weight of the pavement and the weight of the vehicles on top of it, while allowing all this open space for the plant roots to go through. So here's one of these systems being installed next to a roadway. You can tell these work really well, because that is a lot of open space that the plants can now grow through. But obviously something like this is very expensive. This isn't something that's practical for you to do on your own property, but it is the kind of project that local governments are now asking developers to use when they're putting in a new big apartment building, a new shopping center, so they can get street trees to grow along these new roads that are going to look good, that aren't going to just stay small and stunted and die after a couple of years. Because now, because of this extra work and extra expense they went through, those roots have a place to grow, even if it's under concrete and asphalt. And then you have something called flexible paving, and you see quite a bit of this in DC. This is a picture from DC. I really like walking on this stuff. So you're walking down the street, you're walking on the concrete sidewalk, you can feel it very hard. And then you walk on something that looks a little more like asphalt, but it feels much softer than usual. Your feet just kind of sink into it. So it's an asphalt looking thing, but what actually it is it's kind of a rubberized mat that looks like asphalt, but it's got some springiness to it, some give to it. And what this does is it allows the plant roots to grow under, and because it's flexible, it can expand and contract and allow those plant roots to pass through. Better for the plant root, of course, but also better for the infrastructure, because formerly that would have been concrete or asphalt. And as the plant root goes and grows underneath it and grows thicker, it's going to crack up that asphalt. But in this stuff is flexible, and it can swell and shrink to accommodate those growing roots underneath without breaking. So if you are curious about the soil you have on your property, the best thing you can do is check the soil survey. And there's really two places you can go. There's the Web Soil Survey. Web Soil Survey is the U.S. Department of Agriculture's national soil mapping service. So you can find soil maps for, say, about 99% of the counties in the country on the Web Soil Survey. In addition, the Web Soil Survey contains a lot of really detailed ratings tables and suitability tables, so tabular data saying what these soils are good for, what they're not good for. It's not A soil survey map is not going to be specific enough to tell you what you can or can't grow on the soil necessarily. It can give you general advice, but if you're looking for the nutrient content, the pH of your soil, you really do have to get a soils test in order to do that. And I know in Fairfax, you can pick up soils test kits in any public library. I don't know if that's true in Alexandria and Arlington, but if you can make it to the Cooperative Extension Office, they've got free soil test kits there. You send them off to Virginia Tech. I shouldn't say the tests are not free. The kit is free. They give you the kit for free. You do have to send your soil sample off to Virginia Tech and pay them $10 or $12 to do the analysis, which includes major nutrients, pH, and for $2 more, you can get your organic matter content as well too. But if you just want to know some basics about your soil, check out the soil surveys. So this is a picture of the soil survey map that's up on the Arlington County website. And so each of those unique colors and alphanumeric combinations is showing you a different soil type map there along 4 Mile Run in southern Arlington County. That's all I had for today. I'll leave this slide up so you can copy down my email address and phone number if you like. I, of course, will answer questions now, but if a question comes to you in a couple days that you just didn't remember to answer or didn't remember to put out there today, feel free to shoot me an email. Feel free to leave me a message, and I will do my best to try and answer them as well too. But for now, I'll stop sharing. Hopefully anybody who wants that contact information has written it down, and just throw it open to see if there are any questions from folks in the audience.
Dan, there are some questions in the chat.
Okay.
I can go through and read them to you.
Sure.
How do the invasive jumping worms affect soil?
Good question. They eat through the organic matter and sort of the forest litter so quickly, and they burrow through the soil so quickly that they kind of destroy the soil texture. They decompose things faster than normal. So we don't get that nice litter layer, leaf layer on top of the surface, which tends to protect the soil. And it, over time, will create, people call it coffee ground texture, just this really, really fine, almost powdery kind of soil texture that does not have those good pore spaces. It's almost too fine. So when it does rain on that type of texture, it tends to gum up the soil and kind of create a crust on the surface that prevents oxygen and water from percolating down into the rooting zone. So long story short is they kind of destroy the soil structure. And as a result, they eliminate a lot of the pore spaces and good aggregation that a good structured soil would have, and that limits the amount of oxygen and water that can percolate down into the soil.
Okay, another one. In Virginia, is the A horizon only 3 inches deep, even on a forest floor?
Typically, yeah. So, if all humans disappeared, we walked away from DC and came back 100 years later, we would see forests popping up everywhere. We would see old farm fields successioning to mature forests. We'd see trees growing out of buildings and things like that. Naturally, kind of forest is our top successional environment around here. And in our forest soils, our trees are very good at cycling nutrients, storing organic matter within their bodies themselves. So when you go to a forest, there's still a lot of organic matter in the soil for sure. But a lot of the organic matter is locked up in the tree mass, the mass of the wood, the bark, and things like that. If you go to a place like our native prairies in the plains, they're dominated by grasses, and grasses put a lot more of their energy into root growth, and they also exude a lot more organic matter down into the soils through those roots. And they have these very fine, fibrous kind of roots, whereas tree roots are generally, kind of thicker and chunkier. And just the way the grass grows, it tends to put more organic matter into the soil, and it creates that deeper A horizon over time. Whereas in our soils around here, a lot of the organic matter, rather than being stored in the A horizon, is stored within the mass of the tree itself. So not a problem at all. Perfectly healthy soils. But yes, even in a healthy forest, you're lucky to get more than 4 or 5 inches of A horizon. I'd say 2 to 3 inches is about your average.
Okay, next question. Is anyone being innovative in designing or creating construction methods that are less harmful or do less to compact soil? And if so, how?
There might be some folks out there who are. I mean, the problem we have is that the value of land is so high around here that when a developer buys a piece of property, they're trying to put as much house on there since they've already spent $1 million just buying the land. In order to make the money back, they've got to put a big house on there. And that big house takes up a lot of the space. Or, they put in a, small apartment building or something. It's just the land is so valuable, they want to build as much as they can and cover as much as they can. And even if it were not the case, our properties here are small. So even if you put a normal size house on these small properties, the construction machinery is the size it is. If it's working around this 1/4 acre or 1/8 of an acre lot, it's just inevitable a lot of that lot's going to get compacted. So I'll say, even if there are some really good developers out there who are very conscientious, and there are, and they're trying not to compact the soil or trying to limit compaction as much as they can. It's very hard to do that in a densely developed area like Arlington and Alexandria. What you do see some headway with is with county regulations. So I don't know if they do this in Alexandria. I don't think they do. I think Arlington's the only one that does. The reason that we did that study for Arlington that looked at the infiltration rates and the average density of new versus old residences is that the county was thinking of putting forth some new regulations that would require developers to decompact the soil before they sold the house to the first resident, before the first resident could move in. But they needed some proof that there really was more compaction at these new sites versus old, and that it was having an environmental impact. So that's why they had us go out and get the data and kind of design a study to look for that. With that data, what they have done is put in a regulation that's requiring that urban soil profile rebuilding. So that video I showed of the county crew digging and scooping the compost into the soil in the Hell Strip at George Mason Drive, developers have to do that now. So if they're building a single family infill development, putting a new house where an old one used to be, before they sell the house to the first owner, they have to go through and do urban soil profile rebuilding on the lawn, lay out the compost, scoop and dump it in with the machinery that they have there, and then take that machinery off. That's sort of the last thing they do, because that's, if they run over it with machinery again, they recompact it. So it will definitely, it's another thing. It's another cost, of course. I'm sure the developers weren't too happy that they had to do that, but I think it's going to be a very good thing for the soil, and it's going to be a very good thing for the neighbors of that new house, because now they're sitting next to a big new house that at least has functional soil that will be absorbing water instead of sheeting off runoff onto the neighbors on either side.
Let's see, one more question. Is the flexible paving that you mentioned porous, allowing rainwater to permeate it?
I don't know. I'm not sure. I don't know. Yeah, that's a good question. A stumper. There's always one. I don't know. It might be, but it might not. I'm just not sure.
Anyone else has any questions? Just unmute yourself and speak up.
Right. Everybody's looking to get off, probably, which I don't blame you for.
Well, Dan, thank you so much.
Thank you very much.
Thank you.
Always a pleasure to talk to the tree stewards. I'm happy to do it.
It's great. All right. Well, now we all will let that information percolate. Sorry, the pun, bad pun. And anyway, on that, I'm running away. Everybody have a great evening. Dan, thank you again so much, and we'll see you again.
Thank you, Dan.
All right, thank you.
Bye.
Thank you.